Hey everybody, welcome back. This is Calculus 3 with Professor Hefe. We're looking at the cross product. This is 11.4 in Anton. The first video in this section we showed determinants. Now let's just talk about what the cross product is. It is another form of vector multiplication. Dot product was the first form. The second form is vector multiplication with the cross product. And whereas the dot product revealed a scalar, the result of vector multiplication using a cross product is a vector orthogonal to both the first two vectors. This is only defined for vectors in 3 space. You can't do a cross product in 2 space or 2 dimensions. So we're going to look at it. We're going to let u equal u1, u2, u3. V is our v1, v2, v3. The cross product is we're going to use ijk across the top, and then we're going to use our 2 vectors. The way we symbolize the cross product is with an x. So we got u cross v, which is another good reason why we don't use x for multiplication, especially when it comes to doing stuff in calculus. X refers to a cross product. So since it makes a third vector, I'm going to call u cross v, we're going to call it w. And what we do is we take the determinant with ijk across the top, and then u and v. So if you do that, the submatrix for I is the u2, u3, v2, v3. Then we go to the j column. J is the middle one. We minus it. So we've got minus the j times the submatrix u1, u3, v1, v3. Over here, I've been writing the unit vectors at the end because this produces a number. This is a vector. It makes more sense to me. Finally, we look at our third column in the k-hat. Our submatrix is u1, u2, v1, v2. So we could write out w as this. This is another way of writing out w. If you've got u and v listed, u cross v says the same thing. This is just working out the steps. It's kind of easy to notice what's going on here. This is the first component, second component, third component. And notice it just has the 2 subscripts don't have a 1 in it for the first component. For the middle component, the 2 subscripts don't have a 2 in it. And for the third component, the 2 subscripts don't have a 3 in it. For the ones that are supposed to be positive, the number, the first part goes in numerical order, u2, v3. Same thing with u1, v2 at the end. The middle component was negative, which puts these in the opposite order, u3, v1. Because normally when you would do this, you would have negative u1, v3 minus u3, v1. But when you distribute the negative, you get that. So writing it in this form is just the subtraction of the product of each subcomponent that doesn't have the same subscript. I don't have it memorized that way, but it is if you're into that sort of thing. You're good at memorizing things like that, feel free to do so. W is orthogonal to both u and v, even if u and v aren't orthogonal to each other. Okay. Let's look at an example. We'll start with u equals the vector 3, negative 4, 1, and v is negative 2, 0, 6. Let's find w, the cross product of u cross v. So we go through, we put it in. We've got I hat with the submatrix negative 4, 1, 0, 6. Then we go to the j hat one, which is minus the submatrix 3, 1, negative 2, 6. And then we go to the k hat column, which is plus, and then the submatrix is 3, negative 4, negative 2, 0. If you don't write out these submatrix like this, I recommend at least writing out in parentheses negative 24 minus 0 I hat. Then I've got minus 18 minus negative 2 j hat plus 0 minus 8k hat before jumping to that, especially when you're doing a test. It makes it easier for you to go back and check your work. And it makes it easier for me when I'm grading your tests is to see that maybe you just screwed up a simple multiplication here and you said 3 times 6 was 15 and that's why your answer was wrong. If you go straight from the cross product to the answer and I don't know what you did and you don't show any work in the middle, it's kind of hard to give you any credit. Think about that on a test. How can I prove W or vector W is orthogonal to U and V? Think about that for a second before I switch to the next page. Hopefully you came up with what we did in the last section, the dot product. Recall orthogonal vectors have a dot product of 0. So I rewrote down my U and V vectors and I wrote down W. U dotted with W. 3 times negative 24 is negative 72. Negative 4 times negative 20 is 80. 1 times negative 8 is negative 8. We add them up, 0. Bam. U is orthogonal to W. V. Is V orthogonal to W? Negative 2 times negative 24 is 48. 0 times negative 20 is 0. 6 times negative 8 is negative 48. We add those up, we get 0. W is orthogonal to both U and V. And any vector in the plane containing U or V. Because U and V make a plane. Now, it's important to note that the arrangement of the vectors matter. I recommend go back and do V cross U with the vectors we have up above before you continue, just to see what you get. If you do V cross U, remember the V goes along the middle row and U goes along the bottom row. And if you unpause and continue, we can see V cross U. I've got 24 in the I hat direction, positive 20 in the J hat direction, and 8 in the K hat direction, which is the exact opposite of my W vector. So pictorially, when we have U cross V and they're arranged like such, W is going upwards like that. If we've got V and U and they're arranged like such, where counterclockwise like this is like that, W is pointed downwards. Okay. So it's effectively negative W of the first one. If I call this W1 up here, this is negative W1. So both W and negative W are orthogonal to the plane containing U and V, but they point in different directions. One goes out of the plane in one direction, one goes out of the plane in the other direction. Orientation or arrangement matters. A way you can remember it is the right-hand rule. Now I drew a picture. Yeah, I know it's shitty. I'm not an artist. Step 1, you align the U vector with your thumb. This is called the right-hand rule. You can use your hand when you do it. So I'm using my hand. I'm going to align the U vector with my thumb. Then I'm going to align the V vector with my pointer finger. That's my pointer finger. So I've got U here, V here. When I've got it set like that, make your pointer finger and your other fingers make a 90-degree angle. The way your remaining fingers point is the direction of the cross product. U cross V equals W, sticking out. Okay, that's why it's called the right-hand rule. Now, if you're trying to get it to line up with shit on paper, you can get your hand doing some funky, like you can have your hand contorted to try to line stuff up, but it doesn't work with the left hand because your fingers don't bend backwards. So that's how you use the right-hand rule. That's it for our introduction to cross products. Peace, baby.